Howdy, this is your friendly neighborhood physics teacher here, and we're going to go over the multiple choice part on your AP classroom. So what I'm going to do is I'll show you the problem, and then we'll jump to a OneNote and be able to draw and show you what's going on. So this is the first problem. We did do this problem in class, but I would like to go back over it for the ones maybe that were absent, or if it's always good to hear it again. So question 1, rock X is released from rest. So we got some important information that from rest is important information at the top of a cliff on Earth. That is on Earth. So basically what we have going on here, maybe I don't even have to flip back and forth, I can just draw it on here. So you have a rock, you have a cliff, rock X. It's falling. It says it's falling at rest. So that means its initial velocity is 0. So rest just means 0. And since it's on Earth, Earth is telling you that its acceleration due to gravity is negative 9.8 meters per second squared. So we know that it's going down and it's accelerating downward. A short time later, rock Y is released from rest, the same location as rock X. Both rocks fall for several seconds before landing on the ground directly below the cliff. Frictional forces are considered negligible. Basically, all that says is we ignore air resistance. We're in the perfect physics world. There's no air except we can breathe. Yay! Which of the following graphs correctly show the vertical velocity of rock X as a function of time? Take the positive direction to be upward. So since our positive direction is upward, our acceleration due to gravity is down because it goes down. Now, it's asking for what the graph will look like. So we have to know what the rock is doing, not what the rock is cooking. So as the rock falls, is it going to speed up or is it going to slow down? Or is it going to stay constant? Or is it just going to hover there? There's so many things it could be. Hopefully you're like, it's going to end up speeding up because of that acceleration. Remember, the definition of acceleration is just telling you that, because it's meters per second, Oh, did I have the answer? No. Okay. Ignore that. So it's meters per second. So that's just saying every second the rock falls, the velocity is going to either increase or decrease by 9.8. Since the rock is going down and acceleration is negative going down, since they're both going down, it's going to end up increasing. So we need to find a graph that shows that the rock is increasing, and since it says that the direction positive is upward, so it's increasing in the negative direction. It's increasing in the negative direction. So let's look at the first graph. So we got to look at our graph. So it is going down, so it is moving in the negative direction. We're good. We're starting off horizontal and going vertical. Oh, no, hold on. Gotta backtrack real quick. This is it. You have to pay attention to what graph it is before you even start talking. This is a velocity time graph. This is a velocity time graph. Do velocity time graphs curve? Hopefully you just said no. So it's not A. Because velocity time graphs do not curve. I was about to fall in the AP trap and go, oh yeah, here we go. Nope, it's a velocity time graph. Always check to see what graph it is before you start moving things around. So now graph B. So first we're going to check what graph it is. It is a velocity time graph. It is below the x-axis, so that means it's in the negative direction. And the numbers, so it's 0, 1, 2, 3, 4, 5, 6, so on and so forth. So it is increasing in the negative direction. That looks really good to be an answer. Let's double check the rest. So again, this is a velocity time graph. It's above the x-axis, so it's in the positive direction. Not the right answer, because we're looking for something that's in the negative direction. So this is a velocity time graph. It's in the negative direction, but it's showing that velocity is not changing. It's constant. Well, that doesn't work because it's accelerating. There has to be a change in velocity. So it looks like our answer is B. Very good. We're going to clear screen, and we're going to move on to the next question. Let's put my mouse back on. There we go. So question 2. Question 2 is the exact same setup. Question 2 is the exact same setup. We still have rock X falling off a cliff, rock Y falling right behind it. So let's see what the question says. Which of the following graphs best represent the vertical displacement? The vertical displacement of rock X as a function of time, starting immediately after the rock is released from rest. Oh, there's that rest again. So, again, we have rock X falling off of the cliff. We know the initial velocity is 0 because it starts from rest. And since it's on Earth, we know that the acceleration is going to be negative 9.8 meters per second squared. And that negative means it's going down. We've already stated that the rock is going to end up speeding up. The rock is going to end up speeding up. So on a vertical displacement, that's just another way of saying position graph. So for a position graph, what would we need to see? Oh, we need to double check real quick. Okay. Take the positive direction to be downward. They switched our direction. So now it's going to be a positive 9.8 because it says down is positive. So let's look at A. So check what graph it is. It's a displacement versus time graph, the one we're looking for. And if it's going up the graph, it's positive, so we're good there. But then it's going more vertical to horizontal. So if it goes vertical to horizontal, that means it's slowing down. But we need our rock to speed up. So nope, not the right answer. B. Let's look at B. So again, it is a displacement versus time graph, the right graph. And it is going down the graph, so that is a negative direction. And we need a positive one, because it says that the positive direction is down. So let's look at C. Again, it's a displacement versus time graph. It's going up the graph, so it's positive. It starts off horizontal, and it goes more vertical. That means it's speeding up. So it's speeding up in the positive direction. That's looking like our answer. Let's check the last one just to make sure. This is a displacement versus time. We're good, but it's going down the graph. So that means it's a negative direction. So we were right. Yay! C is our answer. Next question. So again, we have a very similar setup, or the exact same setup. Rock X is released from rest at the top of the cliff. That is on Earth. So we still have important information. We still know it's rest on Earth. A short time after, rock Y is released from rest, the same location as X. Both rocks fall several seconds before landing on the ground directly below the cliff. Frictional forces are negligible. After rock Y is released from rest, several seconds after rock X is released from rest, what happens to the separation distance S between the rock as they fall but before they reach the ground, and why? Take the positive direction to be downward. So now we're comparing the two rocks. We have rock X and we have rock Y. We have rock X and we have rock Y. So rock X gets dropped first. So after 1 second, goes here. 2 seconds here. 3 seconds here. And so on and so forth. So let's say after 2 seconds, at 3 seconds, rock Y gets released. So that's 1 second, 2 seconds, 3 seconds. We'll say at 2 seconds. No, we'll say at 3 seconds. Rock Y gets released. So then at 4 seconds, it would be here. And at 5 seconds, it would be there. So at the beginning, yes, for X at 1 second and Y at 3 seconds, it would fall at the same rate. But once Y gets released, X is already way down here. And since we're on Earth and the gravity is negative 9.8 meters per second, right? Meters per second, it's going to end up being, so if we're at 0 up here, velocity 0, then our velocities end up going to be negative 9.8, and negative 19.6, and negative 29.4. That's going to be our velocities. Remember, that's meters per second. So that means for every second, that rock is going to fall 9.8 meters. For every second, that rock is going to fall 19.6 meters. For every second, it's going to fall 29.4 meters. So when Y is released, its velocity is just going to be negative 9.8 meters per second. So at 3 seconds, when rock X is falling at 29.4 meters per second, rock Y is just going to be following at 9.8 meters per second. So rock X is going to end up moving further than rock Y. X is going to be moving further than rock Y once Y is released. So let's look at our answer choices. S is constant because at the moment rock Y is released, the only difference between the rocks is the difference in height above the ground. Well, their height is different, but that's not the only difference. The key thing is only. Physics rarely lives in like absolutes because their velocities are different. Their height is different. So that statement in general is wrong. B states S is constant because the difference in speed between the two rocks stays constant as they fall. Now that is something that you can check. So if you sit there and do a little bit of math and see that 29.4 minus 9.8 and so on and so forth, you do see that the velocities do stay constant because they're constantly changing at 9.8. So we know at least this part of the statement is true. But let's keep going. Because we didn't say it's going to be constant. When we were talking about it, we said it was going to change because at 3 seconds, y is only falling at 9.8, where x is falling at 29.4 meters. X is going to fall further than y, so it's not going to stay constant. So we can go ahead and X that out. S increases because the difference in speed between the two rocks increase as they fall. Again, we can sit there and see that it doesn't if we sit there and do the math. But S increases because at all times, rock X falls with a greater speed than rock Y. At all times, and it is. So at 1 second, it's falling greater. 2 seconds, 3 seconds. So your answer is going to be D. And the big thing about C, yes, the first part was correct, but the big thing about C is the difference in velocities doesn't affect the falling. You have to think about what's affecting the falling. Okay. So we'll clear that. Let's go to question 4. Toy car W travels across a horizontal surface with an acceleration of AW after starting from rest. Toy car Z travels across the same surface towards car W with an acceleration of AZ after starting from rest. Car W is separated from car Z by a distance d. Which of the following pairs of equations could be used to determine the location on the horizontal surface where the two cars will meet and why? Okay, that's a lot. That is a lot of information. So let's break it down. So we have a toy car W traveling across a horizontal surface with an acceleration AW after starting from rest. So it says it's, acceleration. Let me write, please. There we go. We have an acceleration of AW, starts from rest, it's traveling across a horizontal surface. So horizontal surface as much as I can. Then we're going to have a little sombrero car here. So this will be the W, this orange color will be the W. And we have some acceleration. And we know that it's starting from rest. So it's starting from rest. Now, toy car Z travels across the same surface towards car W. So if it's going this way, it'll be going this way. Has an acceleration of AZ and also starts from rest. car W is separated by car Z by a distance, D. So basically here to here is distance D. Which of the following pairs of equations could be used to determine the location on the horizontal surface where the two cars meet? So again, when you're looking at your answer choices, you have to think about what information you have. You have an acceleration, you have an initial velocity, and you have some type of starting point and ending point. But we want to know when the two will meet. So if they're going towards each other, and we don't know if these numbers are the same or not, we want to know when they'll meet. So let's look at A. A states we're going to use our second equation in our formula chart for car W and that same exact equation for car Z. Since the cars will meet at the same time, which, yep, solving for t in one equation and placing the new expression for t in the other equation will eliminate all unknown variables except for x. So basically, it's telling you to use your substitution from algebra. That's basically what it's asking for. It's telling you to do your substitution. Can I scroll down? Nope. From algebra. So you would take one of these equations, solve for t. So you'd make it t equals whatever, and then plug that in for t. So it looks something. So we know your initial velocity is 0. So that can go away. I'll bring this over. So we're left with x minus x naught equaling 1/2 ax t squared. We'll multiply both sides by 2. And divide. Anymore. Okay. So we have 2 times x minus x naught equaling ax t squared, and divide both sides by ax. Then we have to get rid of squared, so I'm going to go ahead and square root. So that will leave us with t equaling the square root of 2 x minus x naught divided by ax squared. And then once you take that, you would plug that in for t. Didn't do that. But you would plug that in for t. Now, B gives you the exact, so saying you would use the same equation for car W, but you would use your delta x, pretty much your displacement equation for car Z. Since the separation distance is known between both cars, the displacement for car Z can be used in the equation for car W so that the time in which the cars meet can be determined. But we're not looking for the time, we're looking for the location. So Once known, the time can be used to determine the meeting location. No, because we can't, just because you know the distance between the two, that's not the displacement of z, because that's saying if you're using that as a displacement of z, the two cars, and it's the total distance between them, you're saying where they'll meet is this car will come all the way and stop there. But we don't know that. So we can't use that equation. I mean, it'd be the same thing for C. C is saying the same thing. You're just using it for car W instead of car Z. It'd be like car Z coming all the way over here and stopping. So like it's not moving. So both of these, B and C, would work if one of the cars wasn't moving. But both the cars are moving. They're accelerating. They both have some type of acceleration. And then D just states you're just using displacement. That doesn't work because, again, you have to take the acceleration, the time. There's too many other variables in the mix. So it has to be A. Okie dokie. Oops. Next question. So this one looks like a projectile problem. So the projectile will not be on the test. Let's see what the question asks. A ball travels with a speed v0, rolls off a desk, and lands in a horizontal position x0 away from the desk, as shown in the figure. The ball is then rolled off the same desk as at a speed of 3 v0 at the horizontal at what horizontal distance will the ball land on the table? So it's asking, so we're not really worried. So we can actually, this problem will help you because we're not necessarily worried about the y direction at all. We're just worried about the horizontal. So think about if it's just rolling. So don't worry about the falling part. The first time it rolls off, your v0 is just v0, and it hits the ground at x0. Well, now we're tripling our velocity. So we're tripling our velocity. How would that affect the distance? To do that, we need to figure out what equation would be the best to use to see what type of relationship the velocity and displacement have. So, if you remember anything about horizontal, there's no acceleration in the x direction, right? Your acceleration in the x direction is 0. So the equation is going to end up looking like that. Your distance equals your velocity times time. So if you increase your velocity, you're going to increase your position or your distance. That's called a direct relationship. So since your velocity increased by 3, guess what? Your distance is going to increase by 3. Yay! Next question. Oops. I'm going to go back to maps. A student drops a rock from rest at a distance h above the ground, such that the rock hits the ground at time t0. At what distance above the ground should the rock be dropped such that it hits the ground at 2t after it's released from rest. So again, this is a similar idea of what we just did. We need to see the relationship of what equation we're going to end up using. So let's think about what givens we have. So we have our initial velocity to be 0. We have that our height is h. We have our time to be t naught. Since it's falling, we know that our acceleration in the y would be gravity, constant. So those are kind of our givens. So looking at our equations, we would end up using our second equation because it has our y final, y initial, plus our initial velocity time, plus 1/2 our acceleration of the y, times squared. It has everything we need. Main thing is we don't have our final velocity, and the other two equations have final velocity. So again, it's trying to see how it compares. So we kind of narrow things down. When it hits the ground, it's going to be 0. So our initial would just be h, plus our initial velocity is 0, so that goes away. So we have 1/2 our acceleration, t naught squared. So let's bring this over, because when you want to compare, you want one thing you're comparing to over the other. So we get a negative equals 1/2 g t squared. But we also know our g is negative, right? Because it's going down. So a negative and a negative, our negatives can actually, our negatives can actually go away. So that is our simple equation. Now it's saying what happens if our t gets doubled. So what happens to our h if our t gets doubled? So this is our basic equation. So now we're going to use that same exact equation, equals 1/2 g. But now we're doubling our t. So that squared would have to go to the 2 and the t. And so we would get, what's 2 squared? Hopefully you said 4. Be 1/2 g t squared. So 1/2 gt squared increases by 4. So there our y, or not y, sorry, our h would have to increase by 4. So again, that's just manipulating the formula to see how you compare. The reason I pulled the 4 out is because I want it to compare to our original equation, 1/2 gt squared, 1/2 gt squared. So what was the difference between this equation and this equation? Was that 4. And since it's a direct relationship, it would also increase the height by 4. Now, your t and your h have a direct squared relationship. It's a direct squared relationship. And the reason it's squared is because your t is squared. That squared affects things. Direct means they both go up. Squared means you have to square your 2 to get 4. There you go. Next equation. Or not equation, next question. So question 7. An object travels along a straight horizontal surface with an individual speed of 2 meters per second. The position of the object as a function of time is given in the table. So time, position. Which the following graph represents the object's velocity, velocity as a function of time. So they give us position, the data table for position in time, but they're asking for a velocity of time. And it also tells you that the initial speed is 2 meters per second. So for a position versus time, how do you find velocity? Hopefully you said slope. So for a position versus time graph, your slope is your velocity. So we need to see if there is a change in your velocity. So you would do, slope, so your change in y over change in x. So your y is your position, so it'd be change position over change in time. And remember, change is just final minus initial. So in this case, your final would be 0 minus 3 over 1 minus 0. So your speed would be 3. Now it starts off at 2, right? So we know it starts off at 2. Oh, so it looks like it's increasing a little bit. So this one would be 8 minus 3 over 2 minus 1. So that'd be 5 over 1. So that would just be 5 meters per second. And this next one is 15 minus 8 over 3 minus 2. So 15 minus 8, 7 over 1. So I think our velocity is increasing. So we need to find a graph that shows that our velocity is increasing. So let's look at the first one. So the first does start off at 2, so that's a good thing. But it's saying it's staying at 2. Well, our data up here shows that it's not staying at 2. It shows that it's increasing. So, not the right answer. Ooh, this one's looking promising. So it starts at 2. At 1 second, showing it went to 4, then 6, then 8. So it's showing that it's increasing. So 3, 5, 7. It's graph is showing pretty close. So that's a possibility. Do velocity time graphs ever curve? Nope, we can cross that one off right away. Velocity time graphs never curve. They definitely don't make an S shape. So it looks like our answer is going to be B. Showing that it's increasing. And there you go. Dun 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 dun. Next question. Oop, forgot to clear it. There we go. So now they're giving us, it looks like an object travels along a straight horizontal surface with initial speed of 2 meters per second. The velocity of the object as a function of time is given in the table above. So now they're giving us a table of time and velocity. Which of the following graphs represent the acceleration as a function of time? So again, to find acceleration for a velocity versus time graph, we're doing slope. So we can do that. So again, slope is just your change in y over change in x. So that'd be your change in velocity over change in time. So we get a 4 minus 2, 1 minus 0. So we get a 2 over 1, which gives you 2. Doing this, 6 minus 4, 2 minus, 1. So it gives you 2 over 1, which gives you 2. That should be meters per second squared. Then we get an 8 minus 6, 3 minus 2, 2 over 1, which gives us 2. I would say our acceleration is constant. Yay! So let's find the graph that shows that our acceleration is constant. Well, acceleration is 2, and it's constant. We're looking at a pretty good answer. Let's check the rest. Acceleration starts off at 2, but it's changing. Nope. No changing. Our acceleration graphs definitely don't curve. And our acceleration graphs definitely don't curve. So, that was pretty easy. So right off the bat, our acceleration graphs would be A. Dun, dun, dun. There we go. Next question. Oops. So question 9. So we have an object X and object Y that's connected with a string, it looks like. We have a graph of acceleration. So it's an acceleration versus time graph. And it's showing you that our acceleration is a -5. Okay, so let's read on. So two objects, object X and object Y, are held together by a light string and are released from rest near a planet's surface in the orientation as shown in the figure. Object X has a greater mass than object Y. It says object X has a greater mass than object Y. So we'll say object X has big M, object Y has little m. A graph of the acceleration as a function of time for the system's center of mass is shown for 4 seconds. Now what it means by center of mass. You treat this, there we go. You're going to treat this as a whole entire unit. So to figure out the center of mass, well, it wouldn't necessarily be the center because object X has a bigger mass, so it'd be kind of sitting, kind of be chilling there. Wouldn't be in the direct middle. It'd be in the direct middle if they had the same mass. But since object X has a bigger mass, it'd be closer to it. So that's, anytime you have a weirdly shaped object that you're treating as one object, like a box connected to a spring, you're going to think about the movement happening there. So think about you have your motion sensor focused on that spot. The positive direction is considered to be upward. Okay. How does the speed of object X, velocity X, compared to the system's speed, the s, after the object has fallen 4 seconds. Now, so we have our little lovely system here, and I'm going to kind of draw them different shapes. And they're falling, right? What's so special? And it says they're near planets. We can just say they're near planet Earth. So we know gravity is negative 9.8 meters per second squared. Think about your free fall lab. Your free fall lab, it didn't matter if you had your marble that was heavier, smaller, it didn't matter. Your accelerations were all about the same. At least they should have come out to be all about the same. So it doesn't matter if you're just focusing on one object, or if you're focusing on a whole entire system. They're going to fall at the same rate. So that means your answer is going to end up being A. Since they're together, it's not like it's going to sit there and start rotating. It's just going to sit there and fall. It's going to fall at the same rate. Because your acceleration due to gravity is always constant. Your acceleration due to gravity is always constant. Okay, question 10. So now we have a velocity. Versus time graph. And it's saying that our velocity is constant. And that's trial 1. For trial 2, we have a velocity versus time. And now our velocity is changing. So we have some type of acceleration. So it says a student uses a motion sensor to collect data of the velocity as a function of time during 2 experimental trials as shown. In which trial does the object have the greatest magnitude of acceleration, and in which trial does the object travel the greatest distance? Okay, so it has a greater magnitude of acceleration. Let's focus on that first. So which trial has the greatest magnitude of acceleration? So if your velocity is constant, what is your acceleration? Hopefully know that your acceleration is 0. Because it's not changing. Your velocity is constant. For trial 2, you have some type of acceleration. You can sit there and do the math if you want to, but we know that acceleration is some type of number. So, greater magnitude of acceleration will end up being trial 2. So that means anything that says trial 1, we can cross out. So we know it's either B or D, because trial 2 has the greater acceleration. So now it's asking for which one has the greatest distance. So finding distance or displacement for a velocity versus time graph, you just do area under the curve. So this just becomes a rectangle. So you just do your area of a rectangle is base times height. Your base is about 5. Your height is 2. So your area is about 10. So it's saying that that one traveled about 10 meters. This one we have a rectangle. a triangle and a rectangle here. So we have two shapes. We have a triangle and we have this rectangle here. So we have two shapes. Let's look at the rectangle first. So base would again be about 5. Your height, so it's going from 3 to 2, says 0.5. And for your triangle, I don't know why I put it, sorry, that should be for rectangle. There you go. For your triangle, it's 1/2 base times height. So again, your base is 5, and your height is 2.5. So then you would just use your calculator. So you do 5 times 0.5, which should be about 2. You get the right color. 2.5 meters. And then you do 5 times 0.5 times 2.5. And you would get 6.25. You would add those together because they're all in the same little unit. Once you add those together, you get 8.75. So your trial 1 is able to go faster. So your answer, dun, 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 is D. Trial 2 has a greater acceleration, but trial 1 is able to go further, not faster. It's able to go further. There you go. Next question. So another linear mass system. So it gives you object X, object Y, center of mass. From center of mass to center of mass is 2 meters, and then from the beginning of object Y in point J is 7 meters. It gives you a velocity versus time graph, and it's of the system. So identical objects, object X and object Y, so that's why the center mass is in the middle, is because both object X and object Y have the same mass, are tied together by a string and placed at rest on an incline. So that's why it starts at 0 as a function shown in the figure. So a distance between the center of mass of each object is 2 meters. The system of the object is released from rest, and the graph of the system's center of mass velocity as a function of time is shown. Based on the data, approximate how much time will it take the center of mass of object X to reach J near the bottom of the incline. Okay, so it gives us the information for the center of mass. So it says the center of mass will hit point J at 4 seconds. That's what the graph's showing. So we know it has to be longer than 4 seconds because the center mass of X is past the center mass. So figure out that much little extra timing there, which would just be 1 meter. So now let's think about what type of data we have. So if we know that it starts from rest, so our initial velocity is 0. We can figure out our acceleration with the graph. So we just need our slope. Changing x, or changing y over change in x. It's just your change velocity over change in time. So final velocity is 8, initial velocity is 0, final time is 4, initial velocity, or initial time is 0. So that gives you 8 over 4, which will just give you a 2 over 1. So our acceleration is 2. So we know that our acceleration is 2. Our distance traveled, so the center of mass, so if it's 7 to the center of object y, and we add 2 more, so 7 plus 2 is 9. So for it to travel object x, our distance is going to end up being, so we have our initial 0, our acceleration to be 2, and to be 9 meters. And we're trying to find time. Again, we're going to end up using our second equation. You'll see that this equation we will use a lot. So our final distance is 9, our initial distance was 0, our initial velocity was 0, we're looking for time, plus 1/2, our acceleration is 2, t squared. So we get 9 equals, that just goes to 1, 9 equals 2 squared. So 3 seconds. 3 seconds. Because 1/2 times 2 is just 1. And 0 times anything is just 0. So those go away. There we go. Next question. So question 12. We have velocity versus time, and we have car y, which car y is, well, it's both above the x-axis, so both of them are moving in the positive direction. So it's a positive direction, and the velocity is getting smaller, so it's slowing down. Car x, again, is a positive direction because it's above the x-axis. This one is speeding up. So just kind of get an idea of what's happening here. So car x and car y travel on a horizontal surface along different different parallel straight paths. So basically, it's just saying that one's, whoops, try that again. One's on this one, one's on this one, so they're next to each other but not crossing. Each car's velocity as a function of time is shown in the graph. Which of the following claims is correct about car X and car Y? Both car X and car Y travel in the same direction. Well, they both travel in a positive direction, so that could be a correct statement. Let's keep going just to make sure. Between time 6 and time 7, car X and Y are in the same horizontal position. So what that is saying, between 6 and 7, they have the same distance. Okay? They have the same distance. So remember to find between 6 and 7. So we'll look at 7. So the area of that one, so that's a triangle, should be 1/2. Base is 7. Height is 7. So base times height. So you get, 7 times 7 divided by 2. So you get about 24.5. But if we're looking at the distance of this triangle, we're doing all of this. So you wouldn't have to do the math. You can just visually see that there's more blue than purple. But just to prove a point, base times height. Again, the base is 7, but in this case, the height is 20. So 20 times 7 divided by 2, you get 70. That's in meters. So no, I would definitely say that they are not in the same position. Car Y is definitely ahead of car X, so no. The change in X's speed per unit of time increases as time increases. Yes. When X, right? I said X speeded up, right? Yep, X speeds up. And the change in Y's speed per unit time decreases as time increases. Okay, so again, let's read that one. Let's read C again. The change in car X's speed per unit of time, increases as time increases. Okay, that, again, ready for some AP wording here? The change in car speed per unit of time increases. So that's saying that at each second, your velocity increases as time increases. Basically, it's saying that your acceleration is increasing, not that your acceleration is constant. So it's all about the wording. That's technically the saying that your speed in the X is increasing, your speed in the Y is decreasing is correct. But that lovely speed of unit of time, that lovely little thing makes it incorrect. because that is talking about your acceleration. And your acceleration is constant, not increasing. So again, lovely AP wording there. B says the magnitude of acceleration of car X is the same as the magnitude of acceleration of car Y. So it's saying that your slopes are the same, and we can look at that and tell that our slopes are not the same. So our answer choice is A. Question 13. This is definitely a projectile problem. Let's look at it anyway. An object is launched upward at an angle of degrees, initial degrees, above the horizontal at a speed of v0. The trajectory, which is just the path, and 3 positions of the object, x, y, z, are shown in the figure. Position x is higher than position z with respect to the ground, and position y is the object's maximum vertical position. Which the following claims is correct about the system that consists of only the object? Okay. So it says the speed of the object at position x is greater than the speed of the object at position z. So it's trying to say x is greater than z. That is incorrect, because z is closer to the ground. Your speed is always going to be, and it says magnitude, right? Okay. So speed, you don't worry about direction. So yes, that's going up. This is going down, but speed, there's no direction. So we don't have to worry about direction. We're just looking at the magnitude. So at position x, it's greater than y. No, because it's going to start slowing down. So as it goes up, it slows down. And as it goes down, it speeds up. Slows down, speeds up. So z would be bigger. The object's speed at point z is v0. So the object's speed at point z is, so it's saying that z is the same as the ground. No, because it's not quite at the ground. Okay. So it would be the same as when the ball is like right there. That would be the same as z. But the initial is right at the ground, so therefore the final would be right at the ground. So nope. The object's acceleration is the same at all points. Because your acceleration in the y is constant, and acceleration in the x is 0. So I would say that's a good answer. The object is at rest at point y. Well, it's at rest in the y direction, but not in the x direction. In the x direction, it's still moving in the horizontal path. So our answer is going to end up being C, because our acceleration is constant. Next question. Okay, so we have a table that's time and vertical position. The table shows the vertical position as a function of time for the object that is dropped from height 5 meters. A student must determine the acceleration of the object. Which of the following procedures could the student use to make the determination? Justify your selections, and then it says select 2. Select 2. So there are 2 correct answers in this mix. There are 2 correct answers. Okay. So let's just go through it. It says create a graph of y as a function of tx. So y, remember this is y, this is t. So create a graph of y as a function of tx, since the slope would be equal to the acceleration due to gravity. So it's wanting you to graph basically your y, so your height, as a function of your t squared. Where that's coming from is your second equation. X equals x naught plus vy naught t plus 1/2 a t squared. So that's what that's where this idea is coming from. So saying that your initial, so if we make your initial 0, and it says it's dropped, and object is dropped from a height student determined, so it's just dropped. So we know that your initial is 0. So you end up getting x equals 1/2 axt squared. So again, remember you can change all your x's to y's. I can get to an eraser. It's wanting to do y as a function of t squared. That's where this equation is coming from, to get your acceleration. But they're not taking the 1/2 into consideration. So that wouldn't work because we still have this 1/2 in the equation. So that wouldn't work. B says use Vy equaling your change in y over change in t to determine the average vertical speed of the ball, and then divide the average speed by the time to determine the ball in which the ball was in the air, since the average speed and time intervals is used to determine the object's acceleration. Okay. So this is, again, thinking, okay, if I find velocity, I just have to divide by time again to get to acceleration. That, you can't sit there, divide by time to divide by time to find acceleration. That doesn't work. That's actually a misconception that a lot of students have. So, because it's telling you to divide by your total time, you've already divided by your total time. You can't really double up on that. So that wouldn't work. So since we have to pick 2, we know that the last 2 are our right answers. But let's go through and prove why it's correct. So using your y equals y naught plus vyt plus 1/2 ayt squared, again, second equation, we've been using it a lot, since all quantities are known except for the acceleration due to gravity. So basically, you plug everything in. We know our final, we know our initial, we know our initial speed, we know our time. So you can actually just plug in to get your acceleration. It says create a position versus time graph of the ball's motion and use data to create a velocity versus time graph of the ball's motion, since the slope of the velocity versus time graph represents acceleration. So make a graph, then make a graph from that graph, and get your acceleration. You can do that. You just can't do it mathematically like B was trying to get you to do. So there we go. Our 2 answers. We're almost done. Woohoo! A student must design an experiment to determine the acceleration of a cart that rolls down a small incline after it is released from rest. So We're looking for acceleration after increase. So we have an incline, we have a cart going down, and it's released from rest. The student has access to a timer, a meter stick, and a slow motion camera that takes a photograph every 1/60th of a second, 60th of a second. The angle that the incline makes with the horizontal is unknown. So we don't know our angle. The length of the incline is unknown. So we don't know which of the following procedures could the student use to determine the car's acceleration. Again, we're selecting 2. So use a meter stick to measure the vertical height of the incline and use the timer to record the time it takes for the cart to travel down the incline. So the height can't be useful because we don't have the angle. So measuring the height doesn't help us to know how far it's going to go because we don't have the angle. We can't sit there and do trig or anything to figure that out. So measuring the height doesn't help. So, nope. Use the timer to record the time it takes to travel along a meter stick that's attached to the incline. So basically, you're using the meter stick to measure the distance and the time. So that at least gets you your velocity, and if you do that at different intervals, that could work. So that's a possibility. C. Use the slow motion camera to film the cart as it rolls down the incline along the meter stick that is attached to the incline. Again, kind of has the same idea as the timer, maybe just a little bit more accurate. Use the slow motion camera to film the cart as it rolls down the incline along a timer to that's attached. So slow motion camera will give you the time, so you don't need a double time. So the answer is B and C. There we go. Last one. So an object is held at an unknown height above Earth's surface, where the acceleration due to gravity of an object is considered to be constant. After the object is released from rest, so the object is released from rest, a student must determine the object's speed the instant the object makes contact with the ground. So, instant contact with the ground. That's our final velocity. Which of the following equations could the student use to determine the object's speed by using the fewest measuring tools? The student does not have access to motion sensors. Okay, so again, we're selecting 2. So we know it's at rest. So we know our initial velocity is 0. We're looking for final velocity. And we want the fewest measuring tools as possible. Since we're on Earth, we know that our acceleration is negative 9.8 meters per second squared. So we're looking for final velocity, we have acceleration, and we have initial velocity. So the only thing we really don't have is time or height. So we would have to measure those. First thing is we need to have an equation that has final velocity in it. So let's mark anything out that doesn't have final velocity in it. Oh, there's final velocity. We're good. There's no final velocity in B, so we can't use B. Oh, there's a final velocity. We're good. There's no final velocity in D. Oh, well, that was easy. So in this one, we had to measure time. This one, we have to measure height. Exactly what we said. So our answers are A and C. Ding, 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 ding. We're done. So that's it for the multiple choice. hopefully me walking through and kind of stepping through, breaking apart, kind of helped you with the wording. Remember, your multiple choice will only have 10 questions, and there's not really much math related. It's, again, mostly graphs. So hopefully that helped. I hope you have a wonderful rest of the day and happy studying. If you have any questions, please ask Miss Templeton. She would love to answer. Have a wonderful day. Remember, you're loved and appreciated. Bye.